Hello, my name is Mohammad Hamza Imran, and today my topic is the central limit theorem and normal distribution. So, today I'll be explaining two fundamental ideas in statistics, the normal distribution and central limit theorem. So, these concepts are the backbone of statistics inference. They help us understand and patterns in data, predict outcomes, and make informed decisions based on samples rather than whole population. So, let's move to the slide why distribution matter. So, in this second slide, every data set has a certain shape called its distribution. So, some are flat and some are skewed and some are from bell shape. So, distribution show us how data values are spread around an average. For example, most people's height or blood pressure tends to cluster around a middle value, with fewer people being extremely tall or extremely short. Understanding the shape of data helps us choose the right tools to analyze it. Now let's moving to the third slide, the normal distribution, the bell of nature. So the normal distribution is one of the most common patterns found in real world data. It's symmetric and bell-shaped, meaning most observations are near this average and very few lie at the extremes. So it's defined by two parameters, the mean, which sets the center, and standard deviation, which controls the spread. For example, including IQ scores, exam marks, or measurement errors in experiments. So this natural balance between common and rare events is why we called it the bell of nature. So now let's moving to the fourth slide, why the normal distribution is so special. So in this slide, the normal distribution has a unique property known as the empirical rule. About 68% of values lies within one standard deviation of the mean, 95% within two standard deviations, and 99.7% within three. So this predictably makes it extremely useful. For instance, if exam scores are normally distributed with an average of 70 and standard deviation of 10, we can say about 95% of students scored between 50 and 90 without looking all their marks. So now let's move to the next slide. The next slide is about understanding standardizations. Standardization is a method to compare different data sets using the same scale. We do this using something called a Z-score. A Z-score tells us how far a value is from the mean in standard deviation units. For example, if a student scores 85 on a test, 85 on a test, and they at a test where the mean is 75 and standard deviation is 5, so their Z score is plus 2, meaning they perform two standard deviations about the average. So now let's move into the next slide, slide number 6, the why sampling exists. It's the most common way that in most cases studying an entire population is impossible. It's too large. That's why we use sampling. Sample is a smaller group chosen from the population to represent it. However, each sample gives slightly different results, and those differences from what we call the sampling distribution. So, by studying the behavior of samples, we can make conclusions about the population as a whole. So, let's move to the next slide, the central limit theorem, CLT. So, this slide is important slide in this presentation. The CLT is one of the most important ideas in statistics. It says that when we take any many random samples from any population, the distribution of the sample means will approximate a normal distribution, even if the original population itself is not normal. So, as the sample size increases, the distribution of those means becomes smoother and narrower. So, in short, averages behave normally when samples are large enough, usually when it is greater than 30. So now let's move to CLT in everyday life. This is our eighth slide. So the CLT is not just theory, it's everywhere. In manufacturing, quality control engineers use it ensure the average weight or size of products stay consistent. So in finance, analysts use it to estimate average daily returns of stocks. In healthcare, doctors use average from patient samples to predict population level outcomes. All this rely on the CLT, which guarantees that averages from samples can be treated as normally distributed. Let's move to the next slide. So this slide is CLT's power from data to decision. This is our ninth slide. Because of the CLT, we can move from data to decision. It allows us to construct confidence intervals and run hypothesis tests. For example, if we take a sample and find that the mean blood pressure is slightly higher than expected, the CLT help us to determine if this difference is just random chance of statistically significant. So I will give an example here. This is a short example. Um, how like this example is the scenario. A company claims that average battery life of its phone is 10 hours. A sample of 40 phones shows us average of 9.6 hours. The conceptual decision is that here we will use the is the company's claim like true using CLT. We estimate how unusual the 9.6 hour mean is compared to claim 10. So here the key message is the CLT allows us to test real world claims using sample evidence without checking every product. So let's move to the slide 11, how normal distribution and CLT connect. So here you can see some key points. I put some here and I will explain it. The normal distribution and central limit theorem are deeply connected. The normal distribution describe how data behaves naturally, while the CLT explain why sample averages follow that same bell shape. Together, they form the foundation of statistical inference, allowing us to estimate unknown population parameters from limited data with confidence. Yeah, here I use applying the central limit theorem. Here is the deviation, and you can see the steps, the step one and step two, and here is the interpretation. And now let's move to last slide. This is our slide 12. So here is the conclusion and reflection. To summarize, the normal distribution explain natural variation. The central limit theorem explain why sample means are predictable. So both allows us to make inferences, build confidence intervals, and test hypotheses. They show us that even though individual data points are random, the average behavior of large samples is remarkably stable. That's the beauty of statistics, finding order within randomness. So here I have explained all this theory throughout. So that's it all from my side. So thank you so much.